This session is machine learning and furnace performance, a powerful future. And really the whole theme about this whole presentation is about, is your furnace running at peak performance? So we'll just investigate that question as we go through this presentation. Because we all know that furnaces are expensive to run. And they use a lot of energy and unfortunately sometimes break down at the most inconvenient times. So with all of that, that gives a strain on the profitability of the heat treatment operation. So what we have to do as businesses to achieve acceptable returns is to actually do continuous improvement to mitigate all of those rising costs. But actually some of the typical continuous improvement activities out there, Kaizen, Six Sigma, etc., they take a fair amount of resource, and we may have already picked sort of the real benefits from them. So where can we go next to find that extra bit of profitability? Is there a better way? And just to expand on that, the economy isn't really helping us that much. If you look at the US economy with a couple of points of GDP growth each year, that doesn't always flow down into the manufacturing plants. So we have no option but to look at what can we do differently to improve, and this is why we look at continuous improvement. So part one of this presentation is actually looking at typical furnace performance issues that are seen across the world, regardless of where you are in the world. Heat treatment is basically the same. You have the same particular performance issues. And then I'm going to introduce a manufacturing framework called OEE, or Overall Equipment Effectiveness, and see if we can use that as a framework to help continuous improvement. From then on, in part two, actually look at how OEE and machine learning together can efficiently help continuous improvement activities and provide profitability back to the plant. Now, typically, some of these things are looked at holistically across the entire heat treatment operation. But I like to think of it that you really need to look at each and every furnace to be able to understand what that profitability is on each furnace, because that can have a major impact to the entire operation of the plant. I'll give you an example from my past. I used to run heat treatment plants in the UK and Asia before coming to the US 8 years ago. And I purchased a second-hand Ostemper furnace for a key customer because they decided to change their process. So we installed this furnace, didn't do a lot of refurbishment on it, started running it. Unfortunately, the amount of product came from the customer varied quite a bit. So there wasn't the demand that we expected from that customer. The furnace actually had some issues with maintenance and also quality. So it took a lot of resource from the rest of the site to focus in on this particular Ostemper furnace to keep it running and keep some output. The other thing is that the furnace was electrically fired, and it also had a nitrogen methane atmosphere, and that's a pretty costly system to run. And in fact, that was actually eating into 50% of the utility costs that we had across the site. So we continued with this and continued pouring in resource to this furnace, and it got to a point sort of a year in with sort of the volumes coming from the customer going up and down that I made a decision it really wasn't profitable to run this furnace anymore. And I had an opportunity. I worked in a group of heat treatment companies, and one of the other facilities decided that they could take this furnace and actually modify it to an oil quench. So they took it from me, which I was quite happy about because it gave instant profitability back to my plant. Unfortunately, a couple of years later, I actually ended up running that other plant, so I met it again. And it wasn't long before I shut it down for the second time, because it was just one of those furnaces that we just couldn't get to run profitably. And it just takes that one furnace to bring all your profits down. You could have the rest of the plant running fantastically, but one furnace, a bad furnace, can cause a real issue. So not all furnaces are like that. And part of looking to the future, looking at different techniques about how we can efficiently improve. If I kind of knew what I now know today with some of the machine learning processes, maybe we could have attacked the issue with that particular Ostemper furnace. But it's still shut down. I think we cut it up in the end, so it doesn't run anymore. So moving on to the key issues. So we've done a number of surveys over the past 8 years. We started with some surveys in the US and then Europe, and the last survey that we did was in Asia, sort of picking the brains of our customer base and also competitors, etc., just to find out what were the key issues regarding furnace performance. And we were able to put all of those issues into 3 real buckets. The first one being furnace availability. So you can see this is the opposite of downtime. So when is your furnace up and ready for product, and when have you got product ready to run through the furnace? When it's down, obviously, and if it's unpredictable downtime, it causes a big strain on everyone within the plant, from production to maintenance to quality, etc. So one of them is furnace availability and unpredictable downtime. The second one is cycle performance. When you typically put in a furnace, you've got a good idea about how the cycle is meant to run, how long it's meant to run, and how much it should cost for that cycle. But as time goes on and the furnace wears, because you're at heat with a lot of furnace furniture, it's starting to slowly destroy itself. So you have to have planned maintenance, but you're going to get things that happen during that process that actually slow down that performance or actually add cost to each cycle. So what can you do to actually improve that situation? You want to get away from these high process cycle costs and potentially wasted energy. And then the third bucket is right first time quality. The worst thing after you've got the first 2 going right is then to process your parts and have an issue with the quality on those components, that you either have to go through some added rework, which is obviously going to cost you more, or worse still, you're going to get reject components. So those are the three issues. And in right first time quality, some of the key things in there are non-compliance issues with standards. You might have the parts that go through the furnace correctly, but if you haven't got all the chart record and all the data to go along with those components, and your customer doesn't accept that batch, it's as if you did a poor heat treatment. And the other one is having an inexperienced team. We've got kind of a different age profile here, but the whole industry is starting to age. We've got a lot of experience retiring out of the industry. So new people are coming in that don't necessarily have the background to heat treatment. So how do we provide that experience quickly to those operators that are just coming into the plant? So it's interesting looking at some of the other manufacturing ways of continuous improvement. There's one called overall equipment effectiveness, or OEE, that's used primarily outside of heat treatment. But it actually fits very well with what we need to do to address performance within the heat treatment setup. So if we remember the last slide, these 3 points that are in OEE, furnace availability, cycle performance, and right first time quality, make up all the requirements of overall equipment effectiveness. And so I like to think about any kind of continuous improvement activity just in very simple terms. Understand where we are now, understand where we want to get to, and then we've got to provide a path from one point to the other. So just giving you some statistics, sort of manufacturers that are struggling, they tend to have an OEE level down in the region of 30 to 40%, which is quite low. Imagine if you had that and then a target of world class, which is 85%, you could easily double your capacity on your site with just looking at improvements on that particular furnace. The actual average for manufacturers is around 60%. So even with 60%, you've still got significant potential to move that 60% up to these world-class levels. So there's significant opportunity by looking at this holistically. However, what happens currently is each of those terms tends to be picked up in heat treatment plants, but they're addressed individually. So you might have the quality department looking at the quality performance across the plant, maybe not on a single cycle. You'll also have, from a production point of view, the production team looking at their metrics. Now, some of these metrics are captured on a paper basis. Some of them are captured digitally. But if you compare what you can actually do with paper records compared to digital data, with paper, once you capture that information on paper, it's more difficult to reuse that information when it's captured on paper. It's more difficult to then take that data and actually enrich it with other information. But if you've got digital data, it makes it much, much easier. So this is why we propose on all of those OEE metrics that if you can capture that in a digital format, it then makes it very much easier to actually control that OEE metric and understand exactly where you are within the process. And if we look at sort of the difference between the people that do this well and sort of the average, it's said by a Gartner study that came out last year that the people that have the best data management will actually outperform their peers by 20%. So that's pretty significant. So that's the first part of the presentation. Really sort of identifying that to eke out that extra level of profitability, we need to look at continuous improvement. One newer method within heat treatment is to look at something like OEE, overall equipment effectiveness, to help you manage that improvement process. But how do we efficiently improve? So this is where we turn to machine learning, and there's a lot of buzz in the world, in the manufacturing world, about the Internet of Things, the industrial Internet of Things, Industry 4.0, and machine learning is a component of that. But it's interesting as we go back in time and look at when machine learning really started. It's been around for a long, long time. If we look at this definition, which is back from the late 1950s, machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. And even that quote is valid today for machine learning activities. Things have moved on a little bit. You do need to provide some kind of programming in your computers to allow the computer system to learn. Maybe at the time they thought the computers will by this time be able to learn completely on their own. Thankfully that isn't the case. So we have to put a framework there, but this is still valid today, that we can actually use computer systems to look at data and actually learn from that data and provide insights. So how does it work? Basically, it's all about having all of this data and being able to find patterns within that data. Now that could be typically in two different areas. That could be trends, or it could be clusters. Now if I take you all back to school, most of us did some work in math around data and looking at best fit lines or clusters of information to provide us some information about if we had new data, how would that new data fit with that particular setup. So instead of us doing it and going back and writing down and trying to calculate it, now the computers themselves can actually take that information in much, much bigger data sets than we could even imagine, and they can sort through it and they can give you that prediction. So let's bring it to something that we all understand in heat treatment, and probably the most crucial thing in heat treatment being temperature control. So what are the issues with temperature control throughout the process? So you're going to really maintain a good ramp rate that's consistent with the requirement for the material. So that can vary depending on your control setup. When you start to hit your set point that you actually want to run at, you've got that period of time where you can have some overshoot. So how do you manage that? How do you minimize that overshoot? And then what you want to do when you've got to temperature, you want to consistently run in a straight line. You don't want to have any deviation around that set point. Otherwise you're wasting energy and you're providing some quality inconsistency. So how do you do that? And then maybe you've got a furnace that you're using at multiple temperatures. So how do you make sure that this is consistent control at all of those different temperatures? Most furnaces are controlled by PID control, proportional, integral and derivative. Now before I joined Eurotherm by Schneider Electric, I ran plants, so I had to learn sort of a bit more detail about the PID algorithm. And there's so many different ways that it's been explained, but probably the easiest way I think about it is thinking in time as far as present, past and future. So if you look at the proportional algorithm, which really does the heavy lifting of the process, that's the present. It's looking at, okay, where am I? What temperature am I at now? What temperature do I need to be? What's the set point? And the difference between the two is the error. And so if that error is large, then my control device needs to give a large output to minimize that error. If the error is small, it needs to give a small output. And proportional does the heavy lifting of the whole PID algorithm. So it gets you close, but it doesn't quite get you right to that set point. There can be still a little error that's left, because when there's a little error, it really doesn't see that it's got enough there to bump up to that set point. That's when we move on to the next term, which is integral. So integral actually looks at the past. It says, okay, how have my errors accumulated over time? Now, have I got enough error that I can give that extra little bump to temperature? So, and actually quite a lot of PID controllers just use PI, and that's it. But D does come in. D with the derivative looks at the future. So if you have some kind of interruption in the process, maybe you've got a two-zone furnace with an inner door that opens and it's transferring from one chamber to another. The inner door opens, you get a sudden drop in temperature. If just the normal algorithm took over, you could be in a situation where the controller actually just wants to put in a lot more heat. But if you've got the derivative equation running, that actually looks at that interruption and is trying to pick out what's the rate of change of my error and how is that going to affect my speed of getting to zero. So if it sees that I'm going to minimize that to zero very quickly without me putting any more output in, it's not going to do anything. If it says, okay, there's been a big change and I need to put in some extra power, that's when the derivative acts on that. So that's PID control, and not all PID controllers are the same. So even within Eurotherm, we have PID sets for, say, the plastics industry, as well as the heat treatment industry, and some simpler methodologies in plastics might only have kind of 10 terms within that PID set. Whereas in the heat treatment industry, our algorithm has 30, 40, 50 plus terms in it. So there's a difference between PID algorithms. And the other thing I mentioned about the different set points, if you run your furnace at different temperatures, how do you cope with that? Because when you tune these furnaces, say if you've got a temper or a draw furnace that has a single burner for low temperature and multiple burners for high temperature, the PID and the control characteristics are going to be very different at those different temperatures. So thankfully in more advanced controllers, you do have the ability to have what are called PID sets or gain scheduling. And so you can use a different set of PID for the low temperature, maybe the mid temperature, and the high temperature. We actually have some OEMs that just use our advanced controllers purely for a commissioning purpose, because they know it makes it much, much easier for them to commission the entire furnace by having that flexibility of PID sets. So we come to auto-tune in heat treatment. So how do we actually take those PID, how do we create those PID constants in the first place? So go back 20 years, when I was running a furnace, I would do this manually, and it would take me hours to actually set up the right PIDs. Then roughly about that time, sort of 20 years ago, with microprocessors going into control systems, that's now developed. So you've got auto-tune, automatic auto-tune that are in control devices. So rather than having to do it manually, these devices can take over. And it's the same machine learning pattern. So you might not think that machine learning is within heat treatment, but it has been for 20 years. So all it's doing, it looks at a set of data, typically termed as a training set of data. It looks for patterns within that data, and then it tweaks those PID constants to give you the best set of PID results. And this is it, just looking at PID auto-tune in practice. So when you run auto-tune on a controller, you're actually seeing that the auto-tune initially looks at the steady state conditions. So it doesn't put any output in that particular process. It just wants to see, okay, collect some data, how is my furnace reacting at that level? And then it starts, okay, I've got an initial set of PID constants, let me use those, heat up to an intermediate set point, assess whether I've got any overshoot or not, then let me cool down a bit, let me heat back up, see whether those PID constants need actually changing, and this is all being done real time on the furnace with auto-tune. Finally, once it's decided it's got a good set of PID constants, it then ramps up to your real set point and has a look to see whether those PID settings are valid. And that's a machine learning process. Another example of this, moving from temperature to sort of atmosphere control in carburizing, is the carburizing cycle, where historically we've got lots and lots of data about carburizing, and this has been used to develop carburizing algorithms that can be used actually in online carburizing. But what we've actually found over time is the biggest thing that makes a difference as far as your quality of result from online carburizing is getting a very accurate view of the carbon level that goes into that particular equation. The equation is pretty robust, and it's been used by a number of manufacturers over a number of years. But if you're not picking up a good carbon level to go into that equation, then you're not going to get a good result. So we've recently done some work on a plant with 12 furnaces. It's been running over a year, and we got some results back from that. And we did something a little bit differently, where we took on each furnace there was a separate gas 3IR analyzer with an oxygen probe, and we had the gas 3IR analyzer producing an IR carbon percentage just from its constituents, CO2 and CH4. And then we had the oxygen probe producing its carbon potential. And then in real time, we're just comparing the two. But instead of maybe in the past, that if we saw an error between those two, that we just step the process factor up or down depending on the difference between those two readings, we'll step it right up to what should be the real value. We actually step it up in very small increments, because this is it's being sampled on a continuous basis. And what we found by doing that and then linking that carbon information into the carburizing algorithm, we've got some very consistent results with online carburizing. And in fact, sort of the initial commissioning results that we ran were within plus or minus 1 thou tolerance on case depth from what was predicted and what was actually achieved on the material. And the company that put this in, what they wanted to do was really reduce the cycle performance, reduce the cycle time, reduce the cycle cost by having a more precise control of their case depth. And so over the period of 12 months that they ran this, they were able to do that, and with the results they got, they saved 9% off their cycle times consistently. So that really gave them some good payback. Looking to the future, there's lots of potential with machine learning to take this into other areas. There are other talks actually going on at the moment looking at predictive maintenance, and this is a particular area that is useful for heat treaters, predicting something before it happens so we can do more planned maintenance on our furnace. But I like to think about this. Think about your best operator that you have in your plant and what they're able to sense with what they see, what they hear, what they feel, what they touch. And try and imagine now with the technology that's available even in smartphones, that those kind of sensors are available to us now within the heat treatment community to do the same kind of thing, but actually through our equipment, through our machines. So whether that's with sort of seeing things with infrared analysis or videos, ultrasonics for hearing things, or acoustic technology, smell, taste, maybe not many operators actually taste their oil, but oil analysis, perhaps more real time than just sending it away every 3 months to get it checked. And on the electrical side, so all the electrical inputs that we get, say from a thermocouple to tell us what temperature it is. We can take all of those signals and track them over time, look at patterns, and be able to improve automatically our process. Cycle performance. So the second bucket, if you look back at the OEE requirement, and in other manufacturing industries, there's a concept of golden batch. So in real time, when we're running the same process, let us look at that process and see where are we against the ideal. And at the end of every single batch, actually alert the operator, the supervisor, the team leader, to tell them, how is my furnace run compared to my ideal? And the final one, right first time quality, making sure you get the quality right through the process first time. And maybe this is looking at sort of the skills of the operator and giving the operator technology aids to help them do a more consistent job, particularly if they haven't got a historical background in heat treatment. So one of the recent offers that we put together in this category was actually for a technician and for a calibration. So we provided a tablet-based calibration system which actually steps them through how to actually do the calibration in the same format each time. And there's some auto alarms on that to make sure that when they put the data in, if it's incorrect, it actually alerts them. But the thing from machine learning is, once we've got that data, we can then look at that period of calibration to the last period, to the period before. We can start to see any drift between those periods, because you have to take the as found results when you do calibration and the as left. So we know what the drift characteristics are. If we know that, we can then predict when is the instrument going to require a service, or when is the instrument needing to be replaced. So much more information can be gleaned from more of that data. How is this all possible? Different levels of solutions. With Schneider Electric, we've teamed up with Microsoft and their Azure platform, which actually has inbuilt machine learning algorithms. So we're on a journey, and we're investigating how far we can use this. With different HMIs, you've got different abilities to do, say, OEE calculations and some mathematical calculations through the HMI panels themselves. Even with the newer PLCs that are available on the market, you can do the advanced calculations within those PLCs. And then from a reporting perspective, there are industrial reporting solutions like Dream Report or SAP Crystal Reports that can be used to extract data and put it in an information format that's meaningful to all of us. How do we capture this data? Various devices, even your controller now has the ability to capture capture tamper-resistant data. You can have dedicated data recording solutions. Also, PLCs can capture data at source. And there's a trend to actually look at the low-cost single-point devices where we might have a particular requirement in a furnace where you just want to have a thermocouple there and quickly and simply get that information to be analysed. And I've looked at a few of these over the last 3 years. Typically the ones that are available out there, they're not quite robust and enough for an industrial practice, particularly in a furnace setup. So we've actually decided to build one ourselves, and we'll be bringing that out later on in 2017. So stay tuned for that.